this is not for you to copy down, it's just to think about it. We need to remember what a cubic polynomial is. Cubic means that your degree is what? Degree is 3, right? So polynomial means the number of terms. It's a lot of terms. So is it possible to have a cubic polynomial function that has no real zeros? Well, first of all, a cubic function, the most basic one, y equals x to the third, when we think about the xy plane, where does it have its end behaviors at? Is it in quadrant 1, 2, 3, 4, all of them? I don't know. Where's the end behavior at? Okay, 3 and 1, right? 3 and 1. That's if your leading coefficient's positive, right? If this is positive, it ends up here and down there. If it were negative, then your end behavior would end up like this, right? But either way, whether it's positive leading coefficient or negative leading coefficient, we know that it goes up and down forever. Isn't that right? Okay. Now, when we say, is it possible for a cubic polynomial function to have no real zeros? What are real zeros? X-intercepts. There you go. X-intercepts are real zeros, answers, solutions, roots, whatever you want to call them. So is it possible to have a cubic polynomial function that has end behavior up here and down here to not cross the x-axis, or up here and down here to not cross the x-axis? No, it has to cross the x-axis, right? Even if it's like way up here somewhere, it's eventually going to cross at some point, right? So it's impossible to have no real zeros. It's going to have at least one. But then again, it could have 1, 2, 3. But anyways, it's not possible for it not to have real zeros because it's going to cross the x-axis. Let's move on. Is it possible to have a quartic function that has no real zeros? What do you guys think? What does quartic mean? 4. So you have y equals x to the 4th. Okay, now if I did have this most basic quartic function, where would it have end behavior at? 1 and 2. That's right. End behavior is up here and up here. So based on that end behavior, there's nothing that tells me that it has to cross the x-axis. I mean, it could be something like this, like down, up, down, like that, like a W, and it's all clearly above the x-axis. So it is possible. Is it possible? Yes, it is possible for a quartic function to have no real zeros. It doesn't cross the x-axis. Okay, so I actually got on Desmos and I typed in that quartic polynomial function, right? And it actually looks like this. And that happened to be a perfect example of a quartic polynomial function that does not cross the x-axis, right? It has no real zeros, okay? So we went over that just to get your brain in the right place. Right now, let's actually take some notes. So let's open up our notebooks and let's jot down the title, Analyzing Graphs of Polynomial Functions, and write down the words relative, max, relative, min. So we should know what a maximum value is, right? It's the max height. If I take this pencil and I throw it up in the air, it's going to go up, 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 and then it's going to reach a max height, then it's going to come back down, right? We know what maximum is. We know what minimum is. But the word relative, does that change it? Well, it does. If I asked you this, is $100 a lot of money? It's relative to the situation, right? If you think about it, the word relative it's relative to the situation. If you're like, hey Dad, I need some money for lunch. Sure, here's $100. That's a lot of money, right? But if you're like, hey Dad, I'm 16, I want my license and I want to buy a car. So he's like, all right, here's $100, right? Totally pointless, right? So relative does make a difference. Now, what does this mean? Relative max, relative min. Like if we look at this graph right here, go ahead and sketch that graph. It doesn't have to be perfect, all right? Just draw an x-axis, draw a y-axis, and just put an arrow down here in the third quadrant and make it go up, down, up, like that. Doesn't have to be perfect. But we know that this arrow down here means that it goes down forever, right? The end behavior is in quadrant 3, okay? Not only that, we could also review end behavior notation. as x approaches negative infinity, f of x approaches what? Okay, we don't remember from last week, huh? As x approaches negative infinity, f of x approaches what? Negative infinity. As x approaches positive infinity, f of x approaches positive infinity, right? Okay, good, good. But anyway, what is the maximum value? Infinity. It goes up forever. So there technically is no maximum value. But there is a relative maximum. If I zoom in and I just look at this part of the graph, it looks like a parabola opening down. And this is technically the relative max to this part of the graph. Does that make sense? So we're trying to understand the difference between your regular absolute maximum value, which is infinity, and if you look at a piece of the graph, and that's the maximum value for this part. So this is what we call relative max right here. So on your graph that you just sketched, go ahead and write down relative max right there and put a dot right there at the top part. And this guy down here, likewise, this one right here is your relative min. Okay? But it's not the absolute minimum because we know it goes down forever. Okay? So that's the difference. And that's not even a definition yet. Let me actually give you the definition here. Here is the definition. I would jot that down somewhere. And you know what? That's my definition. You could write your own. What is relative max or min? It's the max or the min value in a certain part of the graph. Also known as turning points. Okay? So if you look at this graph from left to right, it's going up and then there's a turning point right here. That's a relative max. It's going now down. Turning point. That's a relative min going back up. Okay? Now, let me just randomly ask you other questions here. How many real zeros does this function have? How many real zeros does this function have? It has 3. Okay. What's the degree of this function? The degree is 3, right? So is that a coincidence that there's 3 real zeros and the degree 3? No. I mean, the degree 3 tells you that it could have at most 3 real zeros. It doesn't have to have 3 real answers, 3 real zeros, 3 real x-intercepts. Like, for example, if you were to go to Desmos and type this in and then put like a +3 instead of a +1, it would shift the whole thing up 3 units, and you'd end up with something up here like this, and it would only cross 1 time instead of 3. Does that make sense? Okay. Anyways, let me erase that so we don't get confused. And just to review, as x approaches negative infinity, what do I write? F of x approaches negative infinity. As x approaches positive infinity, f of x approaches positive infinity, right? What is the domain of this, just as a review from semester 1? And yes, that's correct. X equals all real numbers is the domain. So I'm just reviewing things that we need to know anyway. That's the domain. What about the range? Same, but instead of x, we say y equals all real numbers. Again, the domain are your x values. It does go to the left forever. It does go to the right forever. It's just way down there and way up there. And the range is the y values. It does go up and down forever. What else? What else? What if, here's a good one. Here's a good one. What if I told you, could you like verify that this function right here actually represents this graph? Does anybody have any idea on how I could actually like be more sure that, without Desmos, right? Anybody have an idea on how I could be more sure that this function actually represents this graph? This is going back to like Algebra 1. A quick way of verifying any function is to remember in Algebra 1, a function, when you graph it, it represents all the solutions that exist to the equation, right? So this graph right here, if it represents this, it's technically saying that there's an infinite amount of dots all over the place that works for this. So you could, if you wanted to, just plug a number like this one. This is a coordinate what? What is this coordinate? 0, 1, right? So let me actually jot that down. This coordinate is 0, 1. If you wanted to verify that this is this, plug in 0 for your x's, 0 there, 0 there, 0 there. Work it all out. Plus 1. What's your y value going to be? 1. That works, right? 0, 1. You could pick any other point too. You could pick this one right here, which is 1, 2, 3, 1. So you could plug in 3 right there, and right there. Do the math. 3 to the third is 27. 3 squared is 9. 4 times 3 is 36. 27 take away 36. Plus 3 times 3 is 9. Plus 1. And see if it actually gives you 1 as an answer, right? Anyways, I'm just talking a bunch of review skills that we had in the past. But that's not what we're really covering here, but I'm reviewing because I want you to know that stuff. I want you to have that up in your head because it will come out on the test Thursday. Quiz. Man, I'm all confusing right now. Quiz Thursday instead of Friday. Not a test, quiz Thursday. Don't copy this fact down, but let's at least read it. Fact, the degree of a function tells you the most directions the graph can travel and also tells you the most real zeros your graph can have. So it's the same graph, same f of x function. It's a cubic polynomial. This degree is 3, and that's telling me that the most amount of times it could cross is 3. 1, 2, 3. That's the most real zeros you could have. But it doesn't have to be 3 all the time. Again, this could have been shifted up and it only crosses once, right? The degree tells you the most directions your graph can travel. So it's going up from left to right, and then down, and then up. That's 1, 2, 3. So yeah, the degree 3 tells you that at most it could travel up, down, up, 3 different directions. Make sense? Okay. Let's read this. If you're analyzing a graph and the degree of that function must be at least the number of directions that the graph travels, what would the smallest possible degree of this function be? What do you guys think? So if you guys are kind of confused, let's look at this graph however you want, either left to right or right to left. It doesn't matter. I want to look at it left to right. I am obviously traveling down. That's one direction. And then turning point up, that's another direction. That's 2 directions so far. And then down, that's 3. Up, that's 4. Down, 5, 6, 7. So this has to be at least a 7th degree function. It could be 9. It could be 13. It cannot be 5, right? It has to be at least a 7th degree function. Does that make sense? Yeah. Okay. Why? Because it's traveling in 7 directions. 1, 2, 3, 4, 5, 6, 7. So this is at least a 7th degree function. So at least 7th degree function. Okay. How many? How about this? It's a 7th degree function, at least a 7th degree function. We know that it's right off the bat, we know it's an odd degree function because it has an odd amount of arrows pointing up, an odd amount of arrows pointing down, right? But to be more specific, we know it's at least a 7th degree function. So we have something like y equals x to the 7th. But if we did have y equals x to the 7th, an odd degree function, where does it normally have n behavior? Down here and up here, right? In quadrants 1 and 3, right? So the leading coefficient must be negative, right? So I didn't ask this on the question, but yeah, your leading coefficient, it must be negative because it has n behavior up here and down there instead of down here and up here. Does that make sense?
It's going down.
Yeah. It's going down as you go to the right. It's going up as you go to the left. So that means that the leading coefficient must be negative because it got reflected. What else could I ask you just for funsies here? Okay, so this is at least a 7th degree polynomial function. How many real zeros does this one have? It has 3 real zeros. what is the maximum amount of real zeros that a 7th degree polynomial function actually have? The maximum amount of real zeros. 7, right? A 7th degree function could cross the x-axis a total of 7 times. Okay, can't cross 8 times if it's 7th degree function. Maximum of 7 times. So if I were to, like, let's say the x-axis was not right here. Let's say the x-axis was up here. Then you see that it would cross 1, 2, 3, 4, 5, 6, 7, right? That's the maximum amount of times it could cross the x-axis. But obviously, that's not the case. Yeah, what's up? Sure. What is, might as well just write down the end behavior of this. By the way, this negative x to the 7th polynomial function, it can't have all of this fancy stuff in the middle unless you actually have other stuff and make it a polynomial function, right? Okay. So it would never, this guy right here alone, it can't be a 7th degree monomial that has a negative leading coefficient, because that would simply be something like this, right? But when other things happen, obviously you need other things after that in standard form with other items. But what about this? I don't even know the function itself, but I could look at the graph and state the end behavior. So how would I write that? What if I were to write this? If x approaches positive infinity, what do you write next? F of x approaches negative infinity. Good job. And how about if x approaches what? Negative infinity. What am I going to write? F of x approaches positive infinity, right? We need to understand what this notation means, right? This means as you look to the right. As your x's go positive, you're looking to the right. So as you go to the right, this means that it's going down. Your y values are going down. As you go to the right, your y values are going down. This means as you're to look to the left. As your x's go to negative infinity, you're going to the left. Where are your y values going? They're going up to positive infinity. Okay. What is the domain of this guy? X equals all real numbers. What's the range of this guy? Y equals all real numbers. Okay. Do we have, or how many relative minimum values do we have? How many relative minimum values do we have? Relative minimum values. We have 1, 2, 3 relative minimums. Does that make sense? How many relative max values do we have? 1, 2, 3. That's right. Okay. That's a lot of stuff. We're good. All right. So here is the homework that I would like you to practice with. Obviously, our homework is practice. You don't necessarily turn it in unless I tell you, hey, you're going to turn it in. That was the old homework from last week, but let's just jump right into the actual homework. Especially because these instructions could be a little confusing. Part A says, estimate the x-coordinate. This is really weird. Estimate the x-coordinate of every turning point and determine if those coordinates are relative maximum or minimum values. So I'm just going to go to number 34. Where's the turning point at? It's right here. You guys agree, right? That's a turning point. Now, it says approximate the x-coordinate of that turning point. So what is the x value of that turning point? 0.5. 0.5? Negative 0.5 would be right here. 1. It says x, so 1, 2, 3.5. Negative 3.5. So the way they write it, and like I said, this is weird. The way they write it in the answer key, they say negative 3.5. That's an approximation of your x coordinate. And then they say, is it a relative max or a relative min? Relative max. So this is what they put as an answer on the answer key. I would say, give me the actual location, the actual coordinate. They just say the x value of the coordinate. I would say, what is that relative max value? Oh, it's negative 1, 2, 3, negative 3.5, comma, negative half. That's the actual location of that relative max value. They just want the x value of the relative max or min. Could somebody give me a x value of a relative min on this graph, a relative minimum value on this graph? Negative 2.7, negative 2.75, that's absolutely right. Negative 1, 2, negative 2.75. That would get you to that relative min value. So in the answers, it's going to have a negative 2.75 and then relative min. Again, I don't know why they just asked for the x value, but they do. So that's what you're going to be stating. Okay, so you guys could do the rest of those relative min and relative max and the x values. Let's move on to the second thing that they want us to do. Part B, estimate the x coordinate of every zero. What does that mean? What is a zero?
Coordinate of every x.
Yeah. Estimate the x-intercept, right? So on this one, what would we say that our zeros are? Negative, it's almost negative 2, so yeah, negative 1.9.
And negative 0.1.
Negative 0.1 is good. Negative 0.1 is good. What else?
And negative 3.25.
3.25, okay, yeah, that works. 3.25, 3.3, 3.4. Any of those are good. These are zeros. Okay, so that's the second thing they asked for. This next one is probably the most entertaining one for me. It says, determine the smallest possible degree of the function. So I already know that this is an odd function because it's opening up and down. It's not opening, but it goes up and it goes down forever. So it has an odd amount of arrows up and odd amount of arrows down. So I know it's an odd degree function, but is it a third degree function? Is it a fifth degree function? A seventh degree function? Fifth degree is what it has to be at least. It could be 7, it could be 9, but it has to be at least 5. It cannot be 3. How do we know that? The amount of directions it travels in. Goes up, that's 1. Goes down, that's 2. Up, that's 3. Down, that's 4. Up, that's 5. So, has to be at least degree 5. Okay? I could even take this a step further. Is your leading coefficient positive or negative? Positive, right? Because it has the end behavior down here and up here. All right, that's great. What is the domain? Actually, the last thing they asked for is determine the domain and range. So what is the domain of number 34? X equals all real numbers. And what's the range? Y equals all real numbers. All right, cool.
Is it always going to be that?
Good question. Instead of me answering it, let's look at another example like this one right here. All right. Is this an even degree function or an odd degree function? Even. Okay, so right now I'm not following the instructions. I'm not answering what they want us to answer. I'm just asking you anything that you could tell me about this. You guys just said it was even. That's great. We know that even degree functions have end behavior up here in quadrant 2 and in quadrant 1. Unless your leading coefficient's negative, then it would be down here in quadrant 3 and quadrant 4, the end behavior, right? So it is even, but let's be more specific. This even degree function has to be at least what?
6.
At least 6, right? 1, 2, 3, 4, 5, 6. That's right. So at least a degree of 6. Okay. Extra question I could ask you: how many answers could a 6th degree function have? 6, at most 6, right? And this one actually does have 6. It has 1, 2, 3, 4, 5, 6. What else? How many relative maximum values does this have? How many relative max values? 2, right? Right here and right there. How many relative minimum values does it have?
3.
Aha, I got you. 2. This is a relative min. This is a relative min. But this guy down here, it's not just relative. That is the absolute minimum value, right? This is absolute minimum.
Anything except the lowest one.
You see, a relative means that, like, first of all, what's the max value? We can't say because it goes up forever. It's infinity, right? But you could say that this is a relative max because if you just zoom in on this part, that is the max for this part, right? This one over here is the max for that part. But when you look at the whole thing, does it have a max? No, it goes up forever. Now, if you're looking at the minimums, this is a minimum for that part of the graph. This is another minimum for that part of the graph. But if you look at the whole graph, the absolute minimum of the entire thing is this guy right here, right? There is no other point because there's no arrows that point down. Everything is at this minimum value of -5 or above. And that actually brings us to another answer, domain and range. We know domain is x equals all real numbers because it goes left and right forever. But how about the range? Y is
greater than or equal to 5.
-5, right? Cool. So I think we've talked enough about what we need to know. This is not practicing math procedures. This is more of practicing on how to think, right? You look at the graph, and there's many things that you should recognize. Oh, there's 2 arrows pointing up. That means it's an even degree function. I could actually know the minimum degree of that even degree function. 1, 2, 3, 4, 5, 6. Has to be at least degree 6. You know your domain. You know your range from here on up. You know your zeros are where it crosses the x-axis. There's 1, 2, 3, 4, 5, 6 zeros. So we're just stating everything that we can, analyzing these graphs. Now, this is the homework practice that I would like you to do. I already did 2 of them. I would have you guys go back and practice with 35, 36, 38, and 39. The answers are provided. Please check those out. And let's get comfortable thinking this way because I will be giving you graphs like this on Thursday's quiz. And I'll be asking you, like, example, I'll say, if you see this graph on Thursday's quiz, and I'll say, could this be the degree 9? Yes or no? Could it be the degree 9? Could it be the degree 7? Could it be the degree 5? No, it can't be, right? So I'll be asking you questions on the quiz that come from these assignment questions. Good luck.